Welcome to This Explainer. Today, we're taking a fundamental concept and turning it into an absolute superpower. We're talking about dimensional analysis. It's not just some boring unit-checking chore. It's actually a brilliant way to develop deep physical intuition, letting you bypass all that complex math before you even write down a single formula. Let's get right into it. Check out this quote from a 50-year-old math and computer science student on Reddit. They wrote, "I've never really grokked the connections between various things in physics and the calculus that corresponds to them. I always had a hard time translating." Man, that is an incredibly common pain point. So many students struggle to connect abstract equations to physical reality. If you've ever felt that way, you are definitely not alone.
Here's the thing. Textbooks often do it backwards. They just drop these massive, painful differential equations right on your head from day one, leaving you totally confused. Instead of teaching the physical intuition first, they build this intimidating wall of math. Well, today, we're flipping the script. We're going to learn how to quickly pinpoint the physical meaning of formulas without getting bogged down in all those tedious calculations. Section 1, the building blocks of intuition. Okay, let's dive into the fundamental tools we need to start hacking physics. Meet our core tool, dimensional analysis. It's basically a physically transparent method to get approximate solutions and figure out relationships just by tracking fundamental base dimensions. It literally lets us understand the physical reality of a situation before we ever touch the mathematical analysis. Now, in classical mechanics, almost everything derives from just three fundamental letters. Professor Walter Lewin demonstrates this beautifully in his lectures. We've got mass, which we call m, length, which is L, and time, which is T. Literally, any speed, acceleration, force, or energy can be broken down into combinations of just these three letters. It's like a giant puzzle. Exercise 1, the falling apple. Let's move to our first practical exercise and actually use this to train our brains. Imagine you drop an apple. How does the time it takes to hit the ground depend on the height it fell from and the mass of the apple itself? Now here's the catch. You cannot use complex kinematics or differential equations to solve this. Just use your intuition and those basic variables we talked about. Any guesses? All right, here's how we tackle it. Step 1, let's list our variables. We have time, that's T, height, which is a length, so L, mass is m, and the acceleration from gravity, well, that's a length divided by time squared. Okay, step 2. We equate the dimensions on both sides of our theoretical equation. We want time on one side. But wait, look at step 3. This is the brilliant realization. Mass only shows up once. There's literally no other mass on the other side of the equation to balance it out. Because it can't be balanced, mass mathematically vanishes from the whole equation. No way, right? We just proved, without a single differential equation, that heavy objects absolutely do not fall faster than light ones. Just look at the stark contrast between these two approaches. On the left, we have our intuitive result. Time is proportional to the square root of height divided by gravity. We got that just by balancing the letters L and T. On the right, the traditional, tedious calculus approach, using a second-order differential equation. Dimensional analysis gives us this elegant, immediate answer, completely bypassing the painful math. Exercise 2, scaling animal bones. Now, what's really interesting here is how we can apply this exact same superpower to biology. Let's look at a scaling problem. Say a horse is roughly 4 times larger than a raccoon in overall length. How much thicker must the horse's femur bone be so it doesn't just snap under its own weight? Does the bone just get 4 times thicker? Let's use our intuition again. Let's walk through the logic. Step 1, an animal's mass, or its volume, scales proportionally to its length cubed. Makes sense, right? Step 2, the pressure on that leg bone is the animal's mass divided by the cross-sectional area of the bone, which is its thickness squared. So, step 3, to keep that pressure safe and avoid breaking, the bone's cross-sectional area, the thickness squared, has to grow at the exact same rate as the mass, meaning it has to scale with length cubed. So, if a raccoon is our baseline at 1x, the horse's length is 4x. Its mass goes up by 4 cubed, which is 64x. To withstand that massive pressure increase, the bone's thickness squared must equal 64. That means the thickness itself scales as the square root of 64, which is 8. The horse's femur has to be 8 times thicker, not 4. And get this, Professor Lewin actually verified this scaling law using real measurements from the Harvard Bone Collection. How cool is that? Exercise 3, the drag of air resistance. Let's tackle a problem that textbooks usually sweep under the rug because the math is just way too ugly. Physicist Craig Boren poses a really great challenge. How can we elegantly estimate the effect of aerodynamic drag on a falling object without using calculus? Like, if we ignore air resistance, we're making an error. But how big is that error? Here are the steps. Step 1. In the drag equation, there's a constant, b, which is the drag factor. If you look at the units, b has dimensions of inverse length, or 1 divided by L. Step 2. To find our error, we need a dimensionless ratio, so we need a length parameter to counterbalance that inverse length. The only logical length in this falling problem is the drop height, h. Step 3. We simply combine them. Multiply the drop height, h, by the drag constant, b. The lengths cancel out perfectly, leaving us with a dimensionless ratio that elegantly estimates our error. Check out this comparison. On the left, a simple, intuitive multiplication. Our error is roughly the drop height times the drag constant. On the right, a nasty, nonlinear differential equation that you'd normally have to solve to figure this out. We entirely bypass the ugly math just by looking at the dimensions. A real game changer. Section 6. The Buckingham pi theorem. Now, the crucial point here is that this physical intuition isn't just guesswork. It is backed up by a very rigorous mathematical foundation. Enter the Buckingham pi theorem. First proven back in 1878 and popularized by Edgar Buckingham in 1914, this theorem formally states that any physical law can be expressed as an identity involving only dimensionless combinations of variables. Essentially, it proves the universe really doesn't care if you measure things in meters or inches. The fundamental physics remain exactly the same. And it all boils down to this one single, beautiful formula, P equals N minus K. The number of dimensionless groups you can form, that's P, equals the total number of physical variables in your problem, N, minus the fundamental physical dimensions involved, K, things like mass, length, and time. To summarize, this theorem completely solidifies everything we've learned today. It proves physical laws don't depend on unit systems. It lets you compute key dimensionless parameters even if you don't actually know the equation yet. That is literally how engineers test tiny model airplanes to validate how massive jets will fly. And most importantly for us, it completely replaces tedious differential calculus when you just need a solid physical estimation. So, what complex equation can you simplify with your new superpower today? The next time you hit a wall of math and physics or engineering, take a step back. Don't just start blindly calculating. Look at the dimensions first, find the scaling laws, and trust your physical intuition. You'll start seeing the whole universe in a much simpler light. Thanks for joining us on this explainer.